What if I told you that this specific Rubik's Cube is impossible to solve? No matter your skill or patience, you don't have a chance, because a mathematical demon lives inside it that is very good at hiding. Another game that was extremely popular in the late 1800s can have the same frustrating property. There were even prizes set out if you could solve it. The property in question is known as parity, and even after one has proven its existence, as we will do, it still seems somewhat magical, at least to me. But our journey to this strange phenomenon starts with World War I, where soldiers needed some way to occupy their mind in their little spare time. One of the gadgets German soldiers used was called 15 puzzle, nicknamed Geduldspiel für den Schützengraben, or Puzzle for the Trenches. Quite descriptive. It's played like this. There are 15 pieces, or stones, in a 4x4 grid, leaving one space empty. Right now you are seeing the final position one tries to reach, with perfect order and the empty spot in the bottom right. We now scramble the puzzle by continuously sliding the pieces to the empty space. And after some more moves, the puzzle doesn't resemble the initial order anymore. The goal is now to unscramble it, so bring it back to the order it once was. It is fun to try, and there are many websites where you can play this game, and I would recommend you give it a go. It is certainly easier said than done, as one has to avoid screwing up solved parts of the puzzle while working on others. Even though it was used in World War I, the puzzle was created several decades earlier, sometime in the 1870s in the United States, even though its precise origin is unclear. From then on, it quickly gained in popularity. By March 1880, the New York Times reported, "No pestilence has ever visited this or any other country which has spread with this awful celerity of what is popularly called the 15 puzzle. It is only a few months ago that it made its appearance in Boston, and it has now spread over the entire country. Nothing arrests it." Another famous mention of this puzzle was given by the chess grandmaster and puzzle creator Sam Lloyd. In his famous book, many puzzles of similar nature are mentioned, and here on page 235, we indeed find the 15 puzzle. But take a look at this wonderful illustration. This farmer has almost solved it, however the 14 and 15 stones are in the wrong order. This is another reason the game is so captivating. Here the challenge is not to scramble the puzzle in the way we saw before and then solve it, but rather start from this very position and then try to find moves to solve it. This riddle drove people mad. It can also arise when one scrambles the problem not in the way we saw before, but instead puts all the pieces randomly in the grid. Then, when solving it, it can arise that you find yourself in this position. There were even prizes set out if someone could find a way to solve this specific problem, like this reward of $1,000. One poem by the New York Mail reads, "William goes a courtin', with her silent sits, both engaged in sorting, wooed in little bits. Not a word they utter, curious kind o' curtain, now and then they mutter, 13, 15, 14. So what an intriguing problem. A dentist at the time even bought an ad in a newspaper and offered a set of teeth as a reward for a solution. Apparently he wanted a solution at any cost. Or he just wanted to get more customers and was aware of the paper that had proven that it is in fact mathematically impossible to solve this position. No matter how hard you try, you cannot solve it. But why? What is it about this position that makes it unsolvable? Or even, how can one prove that the position can't be solved? As it turns out, there is something intrinsic about this very position that prohibits a solution from existing. In particular, one can make two observations about the number of moves one would need to solve this position if it were possible. For the first part, we will color the squares behind the pieces in this checkerboard pattern. Right now, the empty spot is orange. If I shift once, the empty spot is now green. After any second move, the empty spot is again orange. After the third, green again, then orange, and so on. The color seen changes on every move. This is because each green square is only adjacent to orange squares, and every orange only adjacent to green ones. Now, as the empty space of both the starting and end position is orange, we know that the solution must consist of an even number of moves, as we have orange after every second move. That's the first statement we can prove about a potential solution. So it would be great if there was some other bizarre reason why a solution needs to have an odd number of moves, because then we would have a contradiction, as the number of moves needed can't be even and odd at the same time. So a solution cannot exist. For this observation, we will consider the empty spot as an extra stone. So each move is just the switching of the empty piece with one of its neighbors. In general, when one is given objects in particular positions, like placed on a 4x4 board, and one switches the positions of two of them, that's called a transposition. It doesn't have to be in a grid. It also, for instance, could be in a line. Now, say I want to get from this arrangement back to the sorted sequence from 1 to 6 by only using transpositions, and I will remember the current position down here. That's pretty easy to accomplish. In fact, I can do it by using 5 transpositions. The same could also be done by using only 3 transpositions. Or when we are not in a hurry, by using 9 transpositions. But that's odd. All the solutions involved an odd number of transpositions. And as it turns out, that's no coincidence. If one wants to get from this position to this one, it is only possible by using an odd number of moves. And I cannot express how strange and counterintuitive it is that something forces us to use an odd number of moves. If this seems like it can't be true, go ahead and give it a shot. Similarly, there are cases where it is only possible to use an even number of moves. This phenomenon is known as parity. It is the fact that when one is given an arrangement of some objects, but one wants a different final arrangement, then either all ways to get there consist of an odd number of transpositions or an even number of transpositions. For now, if we just believe that this fact is true, we can come back to the 13, 15, 14 problem and notice that each move is indeed a transposition. It switches the place of 2 pieces where one happens to always be the empty piece. Now, one way to solve this current position using transpositions is just swapping the 14 and 15 tile. This is not an allowed move in the game, but stick with me. As we now know of a way to solve it using 1 transposition, which is an odd number, Parity tells us that any other solution must also consist of an odd number of moves. For instance, we might have this sequence which consists of 7 swappings. And this still holds true when we restrict ourselves to only moves that are actually allowed in a game. As they are just transpositions, the parity argument also applies to them. So parity tells us a potential solution to the 13, 15, 14 problem must consist of an odd number of moves. But coloring the squares behind prove the solution must be even. And as these 2 conditions can't be met at the same time, we have indeed proven that the problem is impossible. So parity is this unintuitive effect that forces us to either only use an even or odd number of moves. Before we explain why that is, let's make a jump in time to 1974, where Erno Rubic invents a similar toy, the Rubik's Cube. Its popularity, similar to the 15 problem, also increased rapidly and is now the best-selling toy of all time. It is much harder to solve a Rubik's Cube than the 15 puzzle, and also there are far more possible scrambles, namely around 43 trillion positions compared to 10 trillion of the 15 puzzle. But how does a Rubik's Cube even work? As so many rotations are possible, it seems that no piece is connected to any other piece, which is sort of right. If we take it apart, we find that it consists of 26 little cubes, all of which either have 1, 2 or 3 colored stickers on them. And each of them is unique, so there are no 2 that are alike. 6 of those pieces only consist of 1 color, which are the so-called center pieces. Those are the only ones that are truly connected to one another via something that looks like this. So their position is fixed, but they can still be rotated. In between 2 center pieces are the edge pieces. But why don't they just fall off? Well, they have those extra hooks that are here marked in red that link them with the neighboring pieces. Last, there are corner pieces, each with 3 colors on them, and again those knobs keep them from falling off. And if one puts them all perfectly together, all of the pieces hold each other perfectly in place even when one of the sides is turned. So a Rubik's Cube consists of center pieces with only 1 colored stick on them, unsurprisingly in the center of the sides, edges with 2 stickers, and the corners with 3 colors. And note, as the centers are locked in place with the other centers, they already determine what color a given side of the cube must have in the end. Now, the thing that I find most interesting about them is that again there exist configurations that cannot be solved. For instance, if we take the two edge pieces, yellow-blue and yellow-red, and just swap their positions around, then the cube we get is impossible to solve. Again, it doesn't matter how much time or energy you put into it. But again, how can one prove that this position is unsolvable? Well, first, we would need some way to get a better grasp on where pieces are and where they need to be. In the 15 puzzle, it was obvious, as each piece had a clear position it needed to be in. But with the cube, it's much harder to keep track of everything. But remember, if we stop turning the cube as a whole and only rotate its sides, we know that the central pieces will always stay where they are. For instance here, yellow will stay on top, blue at the left and red at the right. That's because, as we saw, their position can't change relative to themselves, so they dictate where every other piece needs to go. For instance here, we know we need the edge piece that is blue on one side and yellow on the other, and remember, there is only one piece of each type. Now, we know the solution has to do something with parity and transpositions, so let's talk about what a move actually is. With the 15 puzzle, a move was simply the act of shifting one stone, which we viewed as a transposition of that stone with the empty spot. With the Rubik's Cube, a move is turning one side 90 degrees clockwise or counterclockwise. So it does quite a lot more than just affecting the position of two pieces. However, we can describe it as just applying many transpositions one after the other. For one, corner pieces stay corners, while edges stay edges. So we can view a rotation as acting on corners and edges independently. So when we rotate a face 90 degrees, each of these edge pieces gets shifted to its neighbor. However, we could have achieved the same result with three transpositions, namely 1, 2, and 3. Maybe let's look at it from the top and not have all the edges in the same color. So again, rotating 90 degrees is just the same as transposing first these two, then these two, and then these. Great! Of course, for the same reason, a 90-degree counterclockwise rotation can also be described as three edge transpositions. And also, any rotation on the corners can also be viewed as applying three transpositions. So one move is three edge transpositions and three corner transpositions. Now let's look at the allegedly unsolvable cube from before, where two edges were swapped. We can now make two deductions about the number of moves back to the solved cube, if it were possible. First, let's talk to the corners. They will tell us that they can be solved with zero transpositions, as they are already solved. Hence, by parity, any other solution must also consist of an even number of transpositions. Thereby, the number of moves, which is 3 times the number of transpositions, has to be even as well. But what do the edges have to say? They can be solved with one transposition, and because of parity, all other solutions must also consist of an odd number of transpositions. Thereby, the number of moves must be odd. This is now a contradiction, as the number of moves to solve this cube can't be odd and even at the same time. So at least to me, parity feels like this magic incantation, as it gives us a tool for finding order in chaos, for instance by quite elegantly showing the cube is unsolvable. And good luck proving the same result without parity. So at this point, we just have to ask why parity exists. Why is it when one has things which are in a specific order and a different arrangement they should be in, then either always to get from one to the other take an odd number of transpositions or an even number of transpositions? To start, we now need to keep track of which transpositions are applied. For this, we will draw a diagram like this to indicate that first these two elements change place, then these two, and so on. An obvious thing to point out is that if one reverses this process, hence reverse the order of transpositions, we get right back to where we started. And we will use this fact in just a second. Now, what precisely do we need to show? Well, parity claims that if we have some way to get from one ordering to another using transpositions, and there is a different way to do so, then they both must contain an even or an odd number of transpositions. So either we have both on the left and right an even number of arrows or an odd number. Here comes the first crucial insight. We can now simply reverse the entire right side and then stack them below the left one. Hence we get a way of applying many transpositions that together don't change the order at all. Parity claims that either both of the individual blocks that were stacked consist of an even or odd number of arrows, which is exactly equivalent to them together having an even number of arrows. So we simply need to show if we have a sequence of moves that together don't change the order, then there must be an even number of moves. So why on earth should this be true? Why can't there be an odd number of arrows that gets us right back to where we started? Well, there are different clever ways to proving it, but I want to take a more straightforward approach. We will simply try to get a better idea on what the arrows actually do, because right now this mess of arrows is just pure chaos. So the most natural thing to try is to simplify them. Specifically, we will try to collect all those transpositions that involve the first position and move them closer to the top, one after the other. The first arrow is already on top, so let's examine the second one. Unfortunately, we cannot simply change the order with its neighbor because they have an element in common. You see, when this is the case and we change the order anyway, then we get, after applying them, a different result. However, it is possible to rewrite these left transpositions like this. And indeed, if one applies them, we get the same result. If we apply this trick in our case, we get this. And indeed, the arrow that involves the first element is closer to the top. And remember, this specific rewriting of the first two arrows ensures that together all the transpositions will leave the entire order unaffected. Now with the same trick, we can simplify the sequence again like this. Now there are only two arrows left that involve the first position. We can do just the same, and right now, as these two pairs don't even share a common element, we can just change their order without affecting anything. So we continue moving it to the top until there is only one arrow left to which we can apply the same tricks. However, in the end, we have the same transposition twice in a row, which means the elements get switched and right after get switched again, which means we can just cancel them out. This way we have reduced the number of transpositions by 2. And now there aren't even any transpositions left involving the first position. So let's deal with the second position just in the same way, by moving their arrows to the top without affecting the entire behavior and cancelling 2 of them whenever possible. Eventually, even the second position is devoid of any arrows, so we do the same to the third position. And before we know it, everything has cancelled out. Now, why exactly was that useful? Well, the only way the number of arrows was reduced was when 2 of them were identical and then removed. And as they disappeared in pairs, and we ended up with 0 arrows, we know that the initial number must have been even. Because if it were odd, then cancelling 2 at a time, there should be 1 left. This is a very neat way of showing that the initial number must have been even, without actually counting them. Therefore, the 2 sets were either both even or odd, hence precisely what we needed to show. But now we have to ask if this procedure always works, will always end up with 0 arrows, and if one could get stuck somewhere. Well, for one, by applying our tricks, the positions we are keeping track of are moving continuously to the top. Hence, the only way we could get stuck is if at some point there was only 1 arrow that involves the first position that then can't be cancelled. However, why can't a position like this arise? Well, then some other element would get moved to the first position, but as there is no other arrow that moves stuff back to the first position, we know the 4 will stay in the first position, so the initial order can't be restored. Okay, but why is it in the end we can't be left with a single arrow? Well, a single transposition, almost by definition, cannot leave the elements unchanged. Therefore, if we can move arrows continuously to the top with our tricks, we cannot get stuck at any point, and we cannot be left with 1 arrow. The only way this procedure can end is when there are indeed 0 arrows left. And again, as we removed arrows in pairs, the initial sequence must have been even. This is the reason why parity exists. This is the reason the 15 puzzle is unsolvable, and so is the special Rubik's Cube. Parity is the surprising property that always appears when one moves stuff around. And for me at least, parity still astonishes me and is somewhat unintuitive, even though we now know why it exists. With that, I'll leave you with one last poem. With tearful eyes and angry mien, with wasted form, so thin and lean, with hectic flush that's never seen, except on one who long has been devoid of happiness serene. A box lay near her, white and green, quite full of blocks, one space between. Say maiden, say, what does it mean? I'm working at the Gem 15.